Section 3.8, Newton's method. I have a polynomial here. My polynomial is f of x equals negative 2x cubed plus 7x squared minus 4x plus 2. And what I want to do is I want to take that polynomial, I want to set it equal to 0, and I want to solve it. I want to find all the real roots. How do you do that? This is a very difficult one to solve, I would agree. Why is this a very difficult one to solve?
It's not factorable.
It does not factor using traditional methods, that's true. I can't use the quadratic equation because it's got an x cubed. It's not a quadratic equation. So I cannot use the quadratic formula. There is actually a cubic formula. Anybody know the cubic formula? Me either. And there's actually a formula for a fourth degree. If you have x to the fourth, there's a formula for that too. But there is no formula for powers bigger than that. If you have x to the fifth, x to the sixth, x to the seventh. There is no formula, and it has also been proven that there cannot be a formula. Take complex analysis and I'll tell you. That would be like your second year of graduate school if you're a math major. I saw it a long time ago. I can't remember. It has something to do with Galois theory. Whatever that is.
You can't just modify the idea behind the quadratic.
Correct. It doesn't work. It's been proven it doesn't work. So we want to solve it. What do? We could derive the cubic formula. We're not going to do that. No. That would be a correct answer, but that's not what we're going to do. Other ideas. How could you solve it? We can graph it. Okay, so we can easily solve this with our calculator, can't we? How many answers are there?
At least 3.
How many real answers are there?
1.
There's only one real answer. How do you know there's only one real answer? It only crosses the x-axis once. And in this class, we only care about the real answers. So there's one real answer. What is it? Looks like 3. All right. Let's just check for sure. Calculate the 0. Looks like the answer is x equals 2.9345939. Accurate to 1, 2, 3, 4, 5, 6, 7 decimal places. Now my question is, how did the calculator get that answer? Very carefully, that's correct. Can you be more specific?
I have a wild guess that has something to do with the derivative.
It probably has something to do with the derivative, because that's what we've been talking about for about a month and a half, right?
Yeah.
Probably has something to do with the derivative. Probably had something to do with Newton's method. All right. The truth is the calculator does not use Newton's method, but we're going to talk about Newton's method here. Newton's method is the basis for how computers solve. Since Newton lived, spent a long time, there have been algorithms developed which are much quicker and much more accurate. He was alive in the late 1600s, I believe. So it's been quite some time. All right, so here's what we're going to do. Here's the way Newton's method works. You're going to kind of look at your graph, and you're going to pick an x value that looks like it's somewhat close to the solution. So in this case, I'm going to pick the first value. I'm going to pick x equals 2. Is x equals 2 fairly close to the answer? A little bit. That's not too bad. All right, so I'm going to pick my starting value. I'm going to pick x0 to be 2. And what I'm going to do is I'm going to find the equation of the tangent line at x equals 2. How do I find the equation of the tangent line? I find the derivative. All right. So it did have something to do with derivative. You were right. F prime of x is negative 6x squared plus 14x minus 4. So I plug in 2, and that'll give me my slope. Slope is f prime at 2. That's going to be negative 24 plus, oh, I picked a bad number, 28 minus 4, which is 0. All right, so I picked a very bad number. Why did I pick a very bad number?
Because it's a straight line, right?
Well, all lines are straight.
But it's a horizontal.
It's a horizontal line. Okay. So if you're using Newton's method and you pick a value where your derivative turns out to be 0, it's not going to work.
So that would make that the maximum.
Well, it does turn out there's a maximum at 2,
And that's what it's
and that's why our derivative is 0. All right, so we need to pick a different number. So that one's not going to work, and we'll see why it wouldn't work in a minute. All right, let's pick x equals 3. So this fails. So there's one of the issues with Newton's method. Sometimes it fails. And I didn't mean for this to happen this soon, but this is a good example. This is a good example where Newton's method would fail. Anytime you get your derivative equal to 0, Newton's method isn't going to work. All it means is we picked a bad number. We should not have picked 2. We should have picked something else. We decided we're going to try 3. All right, so once again, I would want to find the derivative. I already found the derivative. So now I want to find the slope of the tangent line. I plug in 3. So that's going to be negative 6 times 9 plus 14 times 3 minus 4. Negative 6 times 9 plus 14 times 3 minus 4. I get negative 16. So there's the slope. I also need the y value in order to find the equation of the tangent line. So how do I find the y value? Plug into the original. So that's going to be negative 2 times 27 plus 7 times 9 minus 12 plus 2. Negative 2 times 27 plus 7 times 9 minus 12 plus 2. Calculator tells me that's negative 1. So the equation of the tangent line, y minus y1 equals m times x minus x1. That's going to be y plus 1 equals negative 16 times x minus 3. All right, so let me graph that equation for you. Y equals negative 16, oops, wrong spot. Negative 16 times x minus 3 minus 1. Okay, so there's my original polynomial, and there's my tangent line. We can't see those very well. Let me do a zoom in here. I want to do a zoom box, actually. And what I want you to notice is, I'm going to zoom in right there. So there's my original curve, and there's my tangent line. What can you tell me about the original curve and the tangent line? They're very, very close to each other, aren't they? They cross the axis at almost the same point. I don't think they cross at exactly the same point, but I think it's very, very close. So a good estimation for the answer would be the x-intercept of the tangent line. And the nice thing is, this is a linear function. It's very easy to find the x-intercept of a linear function. How do you find the x-intercept of a linear function? You plug in 0. So 1 equals negative 16 times x minus 3. So 1 over negative 16 equals x minus 3. So x equals 3 minus 1 over 16. And just for fun, I'm going to convert that into a decimal. 3 minus 1 over 16. 2.9375. Okay, so I want to go back and remember, the calculator told us the right answer should be 2.9345939. We made a guess that the answer should be 3, and we did Newton's method, and now we have that the x-intercept here is 2.9375. Is that pretty close? Pretty good, isn't it? How can I get a better estimation? Take a closer guess. So what's a guess? Our original guess was 3. What's a guess that's closer than 3? How about 2.9375? That was closer, wasn't it? So we're going to call that number x1. x1 is 2.9375. And I'm going to go through the entire process again. I'm going to find the equation of the tangent line. And then I'll find the x-intercept of the equation of that tangent line. And it should give me an even better estimation. Yes? How many times do you have to do this to get to the answer the calculator gives?
Well, I mean, it depends.
That depends. It depends on several things. It depends on the graph itself, the curve. It also depends on your original choice. Okay? So we'll see. We'll do it 3 or 4 times and see how good we are.
Is it possible to get to exactly that point?
Yes. It is possible to get exactly to that point.
When you put this question on a test, are you going to ask us to do it 3 or 4 times?
Yes. But in a minute here, we're going to see that that's not really very difficult. All right. I want you to look at this answer that we had here. What was the 3? 3 was our original guess, wasn't it? What was the 1? The 1 was the... It was the y1 point, wasn't it? The y0 point in this case. And what was the 16? It was the slope. Okay, so in general, let's just write down our tangent line. It would look like that, wouldn't it? If I want to find my equation of my tangent line, it's y minus y1 equals m times x minus x1. M would be the derivative, correct? If we plug y equals 0 in here, we want to solve for x. So let's plug in 0 for y and find the x-intercept. How would you find the x-intercept? Divide by the derivative. So you're going to have minus y1 over f prime at x1 equals x minus x1. And then finally, add the x1. So x is x1 minus y1, which is another symbol for f at x1, divided by f prime at x1. This is called Newton's formula. So we know everything. All we have to do is plug it in. So to find the next guess, I plug in x1. I plug in that number. Then I take x1 and I plug it into my original formula. This is the original formula on top. And then I divide by, I plug x1 into my derivative. Okay. So, x1 is 2.9375. So to find our next guess, we take our current guess, 2.9375. Minus we take 2.9375 and we plug it into our original function. So that's going to be minus 2 times 2.9375 cubed plus 7 times 2.9375 squared minus 4. I don't have enough room here. 4 times 2.9375 plus 2. And then divide by, we got to take that number 2.9375 and plug it into the derivative. So that's negative 6 times 2.9375 squared plus 14 times 2.9375 minus 4. So all I have to do is type all that big mess into my calculator and see what I get. What's that?
Instead of having the whole thing in historic 2.9375 variable and then just plug in variable.
All right. Here's what I'm going to do. I'm going to type in 2.9375. And that's now stored in my calculator as the answer. So I'm going to take that number, answer, minus negative 2 times answer squared, answer cubed, I'm sorry, plus 7 times answer squared minus 4 times the answer plus 2. So that's how I take 2.9375 and type it into my original problem. I don't keep typing it over and over and over again. Divided by negative 6 times the answer squared plus 14 times the answer minus 4. My calculator tells me your next guess should be x2 is 2.937061598. Now do it again. You want to see how easy it is to do it again? Just push enter, and the calculator does it again. Yes? I did minus 14 instead of plus 14? I wish you'd have told me that before. You're right, my answer is incorrect because I have a minus where I should have a plus.
And now you can't go back and change it, right?
But I can do this. Watch this trick. 2.9375. Store that back in the answer, right?
735.
What's that?
It's 9375.
2.9375. Better? All right. Answer. Second enter. Second enter. Second enter. Go back and change that to a plus. I don't have to type it all in again.
Wait, is there anything else?
That was going to be my next question. Did I do anything else wrong? Oh, I hope not. Hit enter. 2.9346. Want the next number? Hit enter again. Want the next one? Hit enter. When do I stop hitting enter? Right there. Those two match, don't they? So that's the best answer the calculator can give me. Is that the same answer we got before?
When you go to the proper decimal place, yes.
Yes, in fact, this one we got from Newton's method is a little bit more accurate, isn't it? It has more decimal places. All right, so how does this work in reality? It's pretty simple. Somebody give me a nice polynomial. X squared plus x squared minus 2. Because x squared plus 2 doesn't have any real answers. What are the real answers to that polynomial?
I mean, x minus 1, x plus 2.
1 times 1 is 2?
I'm having a day.
You're doing as bad as I am today.
Yep. Go ahead.
Plus and minus root 2. Okay? We need to make an original guess. What do you want for your original guess?
1.5.
1.5. All right. So then we go to Newton's method. Newton's method says the next guess, x1, will be x0 minus the original function at x0 divided by the derivative at x0. I'm going to use my calculator. There's my guess, 1.5. So then I need that number, 1.5, minus, I plug 1.5 into the original. So that's 1.5 squared. No, I don't want 1.5. I want answer. 1.5 squared minus 2. So I plugged 1.5 into my original function. Then I divide by, I plug 1.5 into the derivative. So that's 2 times answer. And I hit enter. And it gives me 1.41666667. So x1 is 1.416, repeating. How do I find x2? If I just hit enter again, the calculator is going to take that answer and plug it into that formula for me. x2 is 1.414215686. Hit enter again. Matches already. So x3 would be 1.414213562. Which, if you type square root of 2 into the calculator, is exactly the same number. Questions on that? Either that or you're doing a lot of number crunching by hand. James?
Is it okay if we write a program to just do it if we insert value?
Fine with me. I think it takes longer to write the program than it does to just type it in for each problem.
Save it on the calculator.
Oh, I know what you mean. It takes a while to write the program, though. Okay, so what was wrong a little while ago when I picked the number and my derivative turned out to be 0? How come Newton's method is going to fail when your derivative is 0? You have to divide by the derivative. You'd have to divide by 0. So if you happen anywhere along the process to hit a spot where the derivative is 0, Newton's method isn't going to work. What does that tell you to do? Take another guess. Pick a different starting value and try it again. It'll probably work. But it's possible it will fail. Now, another classic example is Newton's method doesn't always work, even when you don't have derivative of 0. Let's say I give you f of x equals x to the 2/3. What's the answer to that polynomial? What's the x-intercept of that? Actually, it's not a polynomial. What's the x-intercept of that function? 0. How do you know it's 0? You plug 0 in, you get 0, right? 0 to any power is 0. So we know the correct answer is 0. Give me a starting guess. 0.1. So we would have x1 is going to be x0 minus the original function at x0 divided by the derivative at x0. So again, I'm going to use my calculator and see how that works. My original guess is 0.1. So I'm going to have my original guess minus, I take 0.1 and plug it into my original function. Divided by, I take 0.1 and plug it into my derivative. My derivative is going to be 2/3 times, I take my answer. Why do I keep actually typing in 0.1 when I say answer?
Because it's a simple decimal.
Yeah, it's easy to type in. So I want my answer minus, plug my answer into my original function, divided by, plug my answer into my derivative. My derivative is going to be 2/3, and then I'm going to need answer to the what power? -1/3. I do need a parenthesis around the entire denominator. You are correct. Because the denominator has more than one thing. So I do need a set of parentheses around my entire denominator. That wasn't my entire denominator. My denominator started here, and I did put a parenthesis there. All right.
Yeah, but that's for the fraction.
No, the calculator knows. Do 2 divided by 3, and then do the multiply. I don't need to put a parenthesis around that fraction. Calculator says the next correct answer is -0.05. Then it says it's 0.25. Then it says it's -1.25. It's flipping back and forth, but it does appear to be getting closer to 0, doesn't it?
Kinda.
I picked the wrong function. That one's working. It's getting closer to 0. I'm getting e to the -9, which means 8 zeros and then a decimal place. E to the -10, e to the -11. I can keep going, it looks like. It's getting closer and closer to 0.
Yeah,
I wanted x to the 1/3. Try it again. F of x is x to the 1/3. My derivative is 1/3 x to the -2/3. Okay, so once again, I'm going to start with my guess of being 0.1. So 0.1 store into my calculator. I'm going to do it right the first time this time. So I want 0.1 minus 0.1 raised to the 1/3 divided by 1/3 times 0.1 raised to the -2/3. There we go. So 0.1 was my first guess. It tells me the next guess is -0.2. And the one after that is 0.4. And the one after that is -0.8. 1.6, -3.2. What's happening?
Why is it getting bigger?
Why is it getting bigger?
It's getting bigger than getting small, and getting bigger than the rid of.
Right. But in absolute value, it keeps getting bigger, doesn't it?
It's doubling and then turning negative.
Right. And it's getting further and further away from 0, isn't it?
Yeah.
How come?
Because the value you're trying to get to is
Not really.
You can't divide by 0.
True, but I didn't divide by 0.
it because the derivative is negative? The exponent is negative?
Because of the way the graph is.
Because of the way the graph is. What can you tell me about the derivative at 0? It doesn't exist. What can you tell me about the derivative when you get really, really close to 0?
It's different.
It's different, but it's going to be very large. So Newton's method has a problem anytime you have a function where your derivative is getting close to an asymptote of infinity. And that's what's happening here. Your derivative, when you get close to 0, gets really, really large, getting close to infinity. Newton's method tends to fail in situations where you have vertical asymptotes. You don't have a vertical asymptote in this problem, but that's kind of what's happening. The graph is going vertical right at x equals 0. So unfortunately, Newton's method doesn't always work, and that's why I know that the calculator, if I ask the calculator to find the 0 for this problem, maybe it can't do it. Nope, it does find it, x equals 0. So that's how I know the calculator is not using Newton's method. There have been improved Newton's methods developed since Newton lived that it does allow technology to solve other problems. The formulas are rather complicated.
Oh.
It would be very difficult to do by hand. They're designed for computers, correct. Other questions?